This is our presentation for our semester-long project for Computer Networking and Information Technologies 450, Enterprise Solutions and Unified Communications. Our group was called the Mask Managers and comprised of myself, Colton Wiesman, Christian Loukopoulos, Alex Ransom, and Tom Simono.
So, starting off our semester, we kind of heeded the advice of Kevin to label our devices and also label the ports and make a diagram of our network with like the IP addresses that we're going to use for each device so it would be less confusing throughout the semester, which ended up helping a lot because when we first didn't have the labeling the first couple weeks, it was pretty hectic trying to figure out what went where and what devices were what. But then after we got that all set up, we were able to start the initial configurations on the devices. So the first thing we had to do was set up the IP addresses on the devices. So we did IPv4 first, and then we added IPv6 addresses to the ISP network. And we had to make sure that those could communicate between each other. And then for configuring the switches, we configured VTP version 3 with the multi-layer switches acting as the servers and layer 2 switches acting as clients. We also configured trunking on all inner switch links. We configured the VLANs on all the switches, the SVIs for each VLAN in our network, layer 2 ether channels on all switches that had 2 links connected between them, and then we configured HSRP on the multi-layer switches. And then as far as the routing went, we configured EIGRP for the branch and main networks and configured BGP on the ISP network as well as the edge routers for branch and main networks. And then after getting the initial configures done, we were able to move on to the implementation of the virtualization and servers, implementing unified communications and network management, and implementing a wireless system, which we'll go over in this presentation.
Our logical network diagram is as shown. On the top right is the main portion of the network. The top left portion is the ISP section of the network, and the bottom left portion of the network is the branch section of the network. This diagram was completed in Visio and was a huge game changer when completing our project. This diagram shows all of our physical network devices, all of the links between devices, and IP addresses on each link. This diagram was originally designed when we started initial configurations of our network devices towards the beginning of the project. As we added more devices, such as servers, wireless LAN controllers, and wireless access points, we added these devices to the diagram and assigned them IP addresses. This was very helpful to refer back to when troubleshooting connectivity issues or any kind of IP conflicts that we ran into. Next up, we will have Christian discussing the physical devices used in our network.
For our project, we ended up using a lot of physical devices. For our physical device list, we ended up using 6 Cisco 3750 switches, 7 Cisco 2960 switches, 8 Cisco 1921 routers, 2 HP ProLiant DL380G6 servers, 1 Cisco AirCap 3602L K9 access point, and 1 Cisco 2504 wireless controllers, as well as the 4 lab computers and countless wires. I'm going to let Tom talk about our IP addressing scheme next.
Our assigned IPv4 block was 192.168.192.0 with a /18 subnet. This subnet goes all the way until the end of the 168 octet. We then subnetted this further into a /22 address for VLAN IP blocks, as well as /30 addressing for point-to-point links between devices. We also left additional /22 all the way to /30 blocks for further expansion if needed in the future. We were also assigned an IPv6 address block of FD92 with a /64 subnet. We then subnetted this further into a /67 address block for VLANs and office segments. We never implemented the IPv6 on our network, so this address pool is left unused and unassigned, but we did write it down in our network documentation. We have 9 VLANs implemented across our network, VLAN 10 being for HR, 20 for finance, 30 for executives, 40 for users, 50 for guests, 60 for management, 70 for voice, 99 as a black hole for unused switch ports, and 308 as our native VLAN. To update VLANs automatically across our network, we implemented VTP v3 on both our Layer 3 and Layer 2 switches. VLAN Trunking Protocol, or VTP, is a service designed to automatically propagate VLANs across devices. This means that VLANs stay consistent across our network, and we do not have to manually add, delete, or edit on all the devices. We configured a separate VTP domain on each location. The DLS1 switch in all locations is the primary switch for all VTP instances. Both Layer 3 switches in each location are servers for VTP, but the DLS1 switch takes the primary server role. To achieve communication between all VLANs, we configured a SVI, or Switch Virtual Interface, for the management VLAN on each device. We also configured an SVI for all the other VLANs on the multi-layer switches, which we are using for HSRP. While keeping in mind our statements of work to finish our project, we also took some time to incorporate aspects of security. Since switches are generally in more accessible areas as opposed to other network devices, they're important to keep secure from physical attacks. With all this in consideration, here's what we did. We shut down all unused switch ports so that they would be in the administratively shut down state. Furthermore, we took all these ports and put them into a black hole VLAN, meaning that the VLAN is not routed or used for any other purpose. We chose VLAN 99 as our black hole. You can see an example of this configuration in the image on the screen. Wrapping up our discussion on switches and their configurations, we have the switching services. On all multi-link connections between the switches, we have configured Ether channel. We chose to use Port Aggregation Protocol, or PAGP, which is a Cisco proprietary protocol. We put all the ports into desirable mode so that both sides of the link will initiate the negotiation automatically, and the link will always choose PAGP. The initial statement of work requested that we run Hot Standby Router Protocol, or HSRP, on each of the Layer 3 switch pairs in the network. The network design called for 3 separate areas containing 2 Layer 3 switches. After creating all the necessary VLANs, we have decided to put VLANs 10 through 40 as active and 50 through 70 as standby on the first distribution layer switch, and do the opposite on the other switch. Given the fact that our network has many loops, we have configured Spanning Tree Protocol, or STP. Out of the many different versions of STP, we chose Per VLAN Spanning Tree, that's PVST. We chose PVST since we have multiple VLANs that handle multiple different kinds of traffic. This way we can change the root bridge depending on the VLAN. Colton will now talk about our routing services.
Enhanced Interior Gateway Routing Protocol, or EIGRP, was configured on both the main and branch locations. It was not configured on the ISP location. In this project, we opted to use named EIGRP instead of the traditional EIGRP, since we would be implementing both IPv4 and IPv6 addressing on our network. Traditional EIGRP is not capable of running with IPv6 addressing. The main portion of the network was configured with an EIGRP instance name of main, and the branch portion of the network was configured with an instance name of branch. The autonomous system number used for the IPv4 and IPv6 address families was 65510 on the main portion of the network and 65512 for the branch portion of the network. On each part of the network, we advertised the point-to-point links configured between devices, as well as all the IP address pools for each of the VLANs. Border Gateway Routing Protocol, or BGP, was the routing protocol used on the ISP location, as well as all the edge routers in the branch and main portions of the network. The edge routers on these locations were the layer 3 switches, main DLS1 and main DLS2, branch DLS1 and branch DLS2. BGP was configured with an autonomous system number of 64512 on the ISP portion of the network, 65510 on the main portion of the network, and 65512 on the branch portion of the network. At each of these locations, the point-to-point links between devices were advertised, as well as all of the VLAN IP address pools. Static routes were then implemented on the edge routers on the main and branch portions of the network to ensure that ISP traffic was not routed through the rest of our network. After configuring EIGRP and BGP on our network, we were still running into difficulties achieving full connectivity between locations. After some troubleshooting, we realized that it was due to EIGRP operating in stub mode on all 6 of our layer 3 switches. This meant that the layer 3 switches were not sending routing updates through EIGRP to our devices in the branch and main locations. To remove the devices from operating in stub mode, we needed to update the iOS on each of the layer 3 switches. The base iOS that was installed on our switches to begin with did not allow us to change the stub operating mode, so our only option was to upgrade the iOS. To do this, we acquired an iOS image for the models of layer 3 switches we were using that supported enhanced settings, allowing us to change EIGRP from stub mode. We configured a TFTP server hosted on one of our PCs and put the image in the TFTP root folder. Once we had an operational TFTP server on one of our PCs with the image we needed for the switch, we had each layer 3 switch download the new iOS image from the PC. We then used this image to update each switch, allowing us to then remove stub mode from the EIGRP configurations. Alex will talk about our remote connectivity in the next slide.
While remote connectivity was not a direct piece of the project, it was one of the services configured on our network. Due to the COVID-19 pandemic, UW Stout decided to move all classes online post-Thanksgiving break. To continue working on our network after being moved online, we worked to configure remote connectivity to our servers and networking devices. Initially, we used TeamViewer as a means of controlling our PCs located in the lab. We had one PC that had a wired connection to our lab network and a wireless connection to the internet. This allowed us to use TeamViewer to this PC and allowed us to access our servers since the PC had a connection to our internal network. After using this approach for a few weeks, a better option was identified to give us remote connectivity. Our initial setup, only one person was able to work remotely at a time, as we only had one PC that had connection to both the internet and our internal network. We configured jump VMs on our servers to negate the issue. We configured 4 VMs, one for each member of our group. The server itself was hardwired to both our internal network and to the internet. We used these hard connections to create logical connections on virtual switches hosted on our servers. Each jump VM was configured as an instance of TeamViewer, giving us our own personal portal to everything on our network. SSH was configured on all of our networking devices to ensure we would be able to remote into all devices after configuring remote connectivity. This took advantage of the management SBI we had configured on all devices, as it gave us an IP address that we could use to remote into all devices, including our layer 2 switches. We used a 2048-bit RSA key on all devices and also used a unified domain name of 450.com. In the next slide, Colton will be talking about the TFTP server.
A trivial file transfer protocol, or TFTP server, was configured as our infrastructure for automatic backups. This server was designed in order to support automatic backups to receive device running configurations from every networking device hosted on our network. This server is hosted on a Windows Server virtual machine located on our primary server. This primary server is located on the DLS1 Layer 3 switch in the ISP portion of the network. Initially, we intended on using the TFTP server software included with the Windows Server installation. However, we later found out that the software included with Windows Server only supports read operations, not write operations. In our case, we needed each device to be able to write their running configurations to the TFTP server, so we needed to explore other options that allowed write operations from devices. After consideration of a few different TFTP server options, we opted to use a third-party software called SolarWinds. After we finalized the configurations of the TFTP server on the primary server, automatic backups were configured to run on a regular schedule. We wanted to configure automatic backups of each device in case we ran into any issues with a certain device. We wanted regular backups to be configured so we had the peace of mind that backups were being saved without having to worry about manually saving the running configurations of each device. Each networking device was configured to run an automatic backup of its running configuration weekly, occurring every Sunday at 10 p.m. We picked this time since network traffic is very likely to be low at night on a weekend. These backups were configured via a cron job. Cron is a job scheduler set to run certain commands on fixed intervals. Each of the networking devices was configured to send backups to the TFTP server located on a VM on our primary server. An occurrence called backup was configured to run at 10 p.m. on Sunday night in a recurring format. This occurrence then ran another policy list, also called backup, that ran the command show running configuration, and then sent the output of this command to the IP address 192.168.236.50, the IP address of the TFTP server. Alex will next discuss our network monitoring in the next slide.
Next up, we have network monitoring, and we weren't quite able to get this fully functioning. We deployed a Linux VM on the server, and we joined it to both virtual switches, the inside switch and the outside switch, and everything seemed to go good, and we could manually assign it an inside address from the 192.168 address family. But then when it tried to pull an address off the lab network to get out to the real internet, that's where it sat at the connecting stage. So if we were able to get that working in the Linux VM, we would have been able to install Nagios onto that image, and from there we could have followed all their well-written tutorials of how to monitor all the network devices and have them communicate with everything. So that's about it for network monitoring.
For setting up the wireless LAN controller and access point, we first had to configure the VLAN interface on the WLC for our VLAN 40. We then needed to add and set up our wireless LAN controller to act as our DHCP server, since we did not actually have one on our network that the WLC could be able to use and pull IP addresses from. In order for it to act as a DHCP server, we had to enable DHCP and give it a scope of addresses that it could assign to the devices that connected to the AP. After getting the wireless LAN controller set up, we were able to start configuring the access point through the WLC, which actually was a lot easier to do than trying to configure through the AP directly, as the WLC offers a GUI that you can use that makes it a lot easier. We actually did not end up configuring much on the AP due to time restrictions, but we got it visible to devices and they were able to connect to it. The wireless site survey turned out to be really interesting, especially when we were able to map the individual floors of each building and see the signal coverage for the floors. So first off, we decided to use the free heat map software called Echo, which allows you to upload a diagram of a building, and then you can walk through the building and it will track the strength of the APs and turn that into a map of the coverage of your wireless network. We would have loved to been able to use a paid version of the heat map software, as it probably would have been more accurate, but we still got pretty decent readings with the software that we used. So to start off, we uploaded all the floor diagrams into this software, and then we started at one point of the floor and would slowly walk around the halls and sometimes lecture halls if they were open, but a lot of the rooms were actually closed, so we weren't able to go into a lot of them. But we did the best we could, and while doing this, you would click on the map and it at roughly where you were standing or walking at the time, and then it would take a reading. And then obviously the more times you clicked and allowed it to take readings while you were walking, the more accurate it was. So there was a lot of clicking involved with this. And then after getting all those heat maps of the different buildings and their floors, we looked at them and found if there were any trends or just weak points to each floor that we could improve in our wireless design. Then for our wireless design, we took these areas that had lower coverage and made sure to add APs to them so that the coverage would be more even and stronger throughout the floors. Again, we wish we had a heat map software that was paid for so we could have designed our wireless network with that, because then we would have been able to see how the walls affect the APs and see what the coverage was like with our design on a map, actually, because with the paid versions you can actually drop APs on and you can like select the walls and select what material they're made out of, so it would have just been a lot more accurate. But we made do with what we had, and we think that our design for our wireless network turned out pretty good even without that. So we ended up using Ubiquiti APs because of the cost savings while still providing the required specs that we needed for coverage of the buildings. And then after looking at all the different AP options for Ubiquiti and comparing like the performance of each AP versus the cost, we decided that we were going to use two of their APs. The first one we decided to use was their Unify HD access point, which costs $349 a piece, but it uses multi-user, multi-input, multi-output technology that allows the AP to communicate with multiple clients at the same time, which significantly increases multi-user throughput and overall user experience. We also picked this AP because it can handle 350 devices without a problem and has a maximum user capacity of 1,000. And then as far as speeds go, it can give speeds of 300 megabytes per second if there are 100 clients at a max range of 400 feet. So it can give 300 megabytes to each of those clients if there's 100, and then obviously that number goes down as more clients add or join the AP, and also it goes up if there's less clients. And then for the Unify HD APs we ended up using, those were our main APs for wireless network design, and they would do kind of more of the heavy lifting, and most of our network comprised of them. And then for the second Ubiquiti APs, we used the Unified Pro access points that costs $149 a piece, so less than half of the HD APs. But with the cost reduction, obviously there came performance reduction, but that was okay because we decided to use these as kind of filler APs that we could implement in areas that didn't have a lot of traffic. So the Unify Pro APs, it can handle 70 clients with a maximum of 125 clients and can provide 130 megabytes per second if there are 10 clients connected. And then again, that goes up if there's less clients, and then down if there's more clients connected to it. So then for the next slide, I'm going to show you what the survey looks like. Here's a couple of pictures. On the left you have the heat map reading, and then on the right you have our wireless network design. So the picture on the left of the heat map reading is of the Applied Arts first floor. The darker green just means that it was a stronger signal, and then the lighter green obviously means that it was a weaker signal. So the first floor had a pretty good coverage. It was a little bit stronger on the right side compared to the left side, and a little bit of the top side of the building. And then you can kind of see where the software tried to pick up some of those APs on the map as well. If you look closely, you can kind of see those little dots. Those are where we were walking and then where we clicked while we were taking the readings. So after looking at this, we decided that we wanted to try to improve the coverage on the left and upper part of the map, which we believe we did based on the picture on the right, which shows our AP locations with the blue stars being the unified HD APs, which are our heavy lifting HPs and can handle a lot more users and give out more megabytes per second. And then the gold stars representing the unified Pro APs, which were our filler APs for spots that had lower traffic. We also decided to include APs to our stairwells because while we were walking around the campus, we noticed that they didn't really have any in there. So yeah, that's what the survey looks like and what our wireless design looked like. And then we just did this for each floor and building for the Jarvis building, Mike Hills, and Applied Arts building.
Auto Quality of Service, or Auto QoS, is a service that applies more so to voice and video devices than it does to wireless ones. With that being said, there are still ways that you can optimize your wireless traffic on your network. On screen, you will see the configuration of the switch port that connects to the wireless LAN controller. Here we have set the port to be trusted, and we have also modified the bandwidth weights for the 4 queues on the port. This means that the WLC will see better bandwidth rates than other ports in that switch. On the WLC, we have enabled FastLane QoS so that if there are any Apple or iOS devices being used for BYOD, they will have increased performance depending on the application being used. Next, we have our final configuration of QoS on the WLC. As you can see, FastLane is enabled, and the QoS type automatically switched to Platinum or Voice, one of the 4 different QoS types on a WLC.
While we face many walls and roadblocks throughout this project, we feel happy with our final project. All of the services that we were able to implement are working as we expected them to. We also felt that this was a great learning opportunity. It helped tie everything together that we have learned over the past few years. COVID made this project difficult as we lost in-person lab time, but it also helped pave the way to learning more about implementing remote connectivity options. It also helped us learn prioritization of what needed to be completed during our in-person lab time and what could be saved and worked on remotely. We were not able to complete everything as initially stated in the original statement of work, but we are still content with the progress we made and the technologies we were able to implement.